So we're very happy to have virtually Simon Lentner from the University of Hamburg, who will speak about Nichols algebras over non-abelian groups.
Yes, thank you very much for the invitation, being in Prague, at least online. So I'm actually talking about quite old things in some sense, in the sense that many of the things I will talk about were things that I worked on in my dissertation and in a subsequent article. But I also include some current work that I do with Ivan Anciono and Guillermo San Marco, which is somehow giving it a more general perspective. And I include some ideas I had since then to somehow put it a little bit more into perspective and not just put some technical definition. And then maybe if we have some time at the end, I can talk about some applications I have in mind. Work with Michael Kunz on a simplicial complex, which is, I think, after what I talked with Andre, very close to things people in Prague are interested in, and also on some applications to mathematical physics. But if not, then not. So let's please feel any time free to interrupt and ask questions, right? So let's start. So the main object that we talk about is a Nichols algebra. So maybe first the most abstract definition I would give in a more category-oriented audience is let have any object in any braided tensor category. So it's a category, any category with some tensor product and some braiding. So X tensor Y is mapped to Y tensor X. Already in this context, we can basically construct the Nichols algebra. Namely, what we do is it is the smallest Hopf algebra in this category. So there's a notion of a Hopf algebra inside a category with a braiding. So you need the braiding for the bi-algebra axiom. And you want the smallest Hopf algebra generated by the object X, such that the coproduct on X is like a Lie algebra. So delta of any element in X is 1 tensor X plus X tensor 1. So you can imagine this very hands-on. So you can take the tensor algebra of X, that's most certainly an algebra in any category, and it has a Hopf algebra structure. If you just define what the coproduct on X is, and then you extend it to products using the braiding, and that's a big Hopf algebra, tensor algebra. And now you can ask whether there is quotients. So you start quotienting down as long as you can, right, without quotienting anything in degree 1. So you take a lot of quotients, and maybe that terminates at some point, right, or maybe not. So that's the universal definition. So it shows you all the structure that Nichols algebra has, and for the proofs, this is, I think, very important. And already at this point, an important but trivial example is if you have a symmetric braiding. So if the double braiding is the identity, then the Nichols algebra is nothing more than, well, basically the symmetric algebra in X, but not symmetric, but sort of braided symmetric. But of course, we're interested in more cases than just symmetric braiding. So then the Nichols algebra is considerably more difficult. But that's maybe the first approximation to think about it, right? It's a now for definiteness, we now go to diagonal braiding. So diagonal braidings means so we have explicitly a vector space X or V with some basis x1 till xn, and a braiding is defined by we switch xi and xj by putting a scalar in front of it and switching the tensor factors. So it's a very easy type of braiding. You can see whatever numbers qij you take, it is a braiding. So maybe qij should be non-zero, so it's invertible, but any choice of numbers qij for all I and j suffice. Again, of course, I can take plus or minus 1. Then I get braided commutative algebra. I get exterior algebra or symmetric algebra. But already we get very non-trivial cases if we choose different numbers qij. And the main source where I think the definition actually comes from, and what is the main application we always have in mind in first approximation, is let's start with a semi-simple finite dimensional Lie algebra G. Then to this attached to some combinatorial data, namely simple roots alpha 1 till alpha n, a root lattice, a certain inner product, a killing form. And we also take some choice q, some complex number, and we define a braiding, which is basically if I switch I and j, then I get the number q to the alpha I alpha j, right here. You see my mouse pointer, right? Q to the alpha I, alpha j. And already this braiding is quite non-trivial. And in fact, what you can check, what it produces is, as a Nichols algebra, the quantum Borel part of the small quantum group. So if Q is a root of unity, it's a finite dimensional thing. If Q is not a root of unity, it's the quantum group. So there is no small, it's an infinite dimensional Hopf algebra, yeah. So maybe that's sort of the entrance, so to speak. There is a very different but equivalent definition that I like because it's very hands-on, also because it's what we use in the mathematical physics application, and also because it doesn't use anything about Hopf algebra. So if you don't know what a Hopf algebra is, we can start maybe on this slide and say what a Nichols algebra is purely on an algebra level. But it's more involved in some sense, but on the other hand, it's much more concrete. So let's try to define a Nichols algebra in this combinatorial way. How does this go? So the first thing we need is the Matsumoto section. So what we can do is, suppose we have a braid, right? So something that starts with n strands and there is some overcrossings. We can, of course, associate to this a permutation. Namely, we simply record where our strands go to, right? How they are permuted, but we forget how the braid looks like. So it's a very, very obvious group homomorphism from the braid group to the symmetric group. This group homomorphism does not split. So there's no good section, because if you have like a transposition here, right, switch on to, where do you send it to? You cannot switch it to the braid because the braid has infinite order while the transposition has order too. So there is no group map in the other direction, but there is a funny section of sets which is defined as follows. So I send a transposition in Sn to the overcrossing braiding, maybe overcrossing. I could also choose undercrossing, but let's define, we take overcrossing. And then we map a reduced expression, so a shortest expression in terms of neighboring transpositions of a permutation to the respective product of braidings. And there is a little lemma in here, which is actually not so trivial, which says that this is independent of the choice of the reduced expressions. So it's not a group homomorphism because the product of two reduced expressions is not reduced. It does not have shortest length. But if it has shortest length, then it's multiplicative. So it's like partially a group map. And the point is, why is this well defined? So why is this independent of the reduced expression? Well, this is due to a theorem of Matsumoto, which says that to go between two reduced expressions of Sn, all you need is relations that you have in the braid group. So somehow, even Sn has more relations, they are sort of, namely transposition square is 1. You don't need this relation to come from one reduced expression to the other. That's a theorem of Matsumoto, and that's basically exploited by this definition. So let's look at a very explicit example. So how does this look for S3? So S3, there is a big braid group in 3 strands. So it's all braids in 3 strands. And this is mapped to permutation S3. And there are 6 permutations in S3. How does the Matsumoto section looks like? The trivial permutation is sent to the trivial braid. The transposition 1, 2 is sent to the overcrossing of 1 and 2. The transposition 2, 3 is sent to the overcrossing braiding between 2 and 3. And now, of course, we extend to products. So 1, 2, 2, 3 is sent to, well, we first braid 2 and 3, and then we braid 1 and 2. And vice versa for this. So 2, 3, 1, 2, we first braid 1 and 2, and then we braid 2 and 3. And now if we take products of length 3, you notice what I just said, namely 1, 2, 2, 3, 1, 2 gives you this braid, if you concatenate these 3 braidings. And the other way around, 2, 3, 1, 2, 2, 3 gives you this braid. But in S3, these are 2 different expressions for the same element, namely for the element 1, 3, right? You switch 1 and 3 and 2 stays. So, but also the braids are the same. If you look at this picture and this braid picture, then all you have done is you pull this string to the other side. So that's what I mean with well-defined, right? It maps any reduced expression of this element 1, 3 to the same braid, well, up to relations in the braid group. So that's the Matsumoto section. That's a very important and non-trivial thing. And somehow the Nichols algebra, I mean, very figuratively speaking, somehow measures how much this Matsumoto section is not a group homomorphism.
Can I ask a question?
Please.
Yes. So it's not clear to me why this the image of 1, 2, 2, 3, 1, 2 is equal to the image of 2, 3, 1, 2, 2, 3, because you are making a choice, right? When you associate a transposition to a braid. And who tells me that the choices that you're making are actually, you know, there is no reason why they should lead to the same element. You see what I mean?
Yes. So that's exactly the point about sort of what's hidden in the definition. So what I say is I associate to each transposition the overbraiding. I mean, I could also take the underbraiding.
No, I see. So you are defining in that you are using the definition to, I see. I'm sorry, that was not, okay, thank you.
No, it's exactly the point. And but you get two different expressions, two different products of three braids. And the fact that they are the same is exactly the fact that this is a relation that still holds in the braid group. So somehow in SN, you have more relations, but these relations are only for reducing expressions. But to go between two different reduced expressions, you don't need them. And that's the content of Matsumoto's theorem, and that's non-trivial, right? It could be that you have to use this relation 1, 2 square is 1 a couple times to make the thing larger, and then use other relations and then reduce again. But that is not necessary. You can use the relations that still hold in the braid group to go from one reduced expressions to the other. And that's the content of the definition. And that's non-trivial. And as I was about to say, the sort of in situations where what we do S behaves like a group homomorphism will be trivial. This is exactly this symmetric case. That's why it's called symmetric group. But somehow we now exactly get expressions that are non-trivial because that's not a group homomorphism. So that's the combinatorically, if you want, the point about Nichols algebra. So categorically, I've made the point, and I try now to make it combinatorically. So let's now take, again, for definiteness, let's just take a vector space and a braiding map. So it's a linear map from V tensor V to V tensor V, which respects the typical equation you have, right? If you cross, 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 it's the same as the other way around, which we just had. Now, you have such a braiding, it gives you an action of braid group in any number of strands, K, on K copies. Oh, it should be X here, of course, I'm sorry, change notation. So it gives you an action of the braid group in K letters or K strands on K tensor products. Namely how? I mean, I just switch the braiding 3-2 switches the second and the third tensor factor here using this map. So this is an action of the braid group. And now we use the Matsumoto section to pull this back to something we can do to permutations. So any permutation is mapped to the sort of shortest braid realization, to the section we just defined, and then we let it act. So this gives an endomorphism for any permutation on this, namely exactly the 6 endomorphisms I wrote down in the previous slide. And now we define the Nichols algebra as follows. We take the tensor algebra again, and now we get an explicit kernel that we divide out, namely the kernel of the so-called quantum symmetrizer map. So what we do is we add up over all permutations what is the shortest braiding realizing this permutation, that's the Matsumoto section, and then let this act on K copies of the vector space we start with by doing what the braiding does, right? It braids factors. So for example, and of course, this is a map, a linear endomorphism in each degree. So it's on X square, on X cube, and so on. And we divide it out. It's not by any means clear that this is an algebra, this is an ideal, right? But it is, it can prove. You divide this out. So for example, SHA2 is you take the identity. This is what you apply. So the identity in S2 is mapped to the trivial braid, and this is doing nothing. And the transposition 1-2 is mapped to the overcrossing braiding 1-2, and this acts by the braiding. So this is an endomorphism on X tensor X. And we divide out the kernel of this endomorphism, right? So that's this construction that goes back to Voronovich in that interpretation. And sort of there's several definitions, some very categorical, some very combinatorial, like here, we don't use any Hopf algebra at all, but they all lead to an equivalent notion. And I think that's why this notion is so universal. I mean, it's a universal object in the tensor category, a universal Hopf algebra, and at the same time, it's something very natural you associate to braid group stuff. Yes, so it's theorems that these things coincide. So let's now look at examples. I think once we have a definition, they should look at examples. So let's first do the one-dimensional case. So let's have a one-dimensional vector space with a braiding Q11, right? It's a one-dimensional thing with a generated span vector x, and we send x tensor x to q x tensor x. So that's all that happens. Now, what I claim is the Nichols algebra is the following quotient of the free algebra. It is usually the free algebra, so there's no relations, except if Q is a primitive L through the unity and not 1, then it's truncated by this relation x to the L. So x to the L is 0. And let's now try to see this explicitly from the Voronovich definition. So let's compute this quantum symmetrizer we just introduced on the only element we have in degree k, namely it's x tensor x tensor x tensor x, right? There's this one-dimensional space in degree k. It's just the x to the k, right? Now, how does the quantum symmetrizer work? Again, we sum over all permutations, go to the Matsumoto section. So there's some braid with n overcross, with k overcrossings, with some number of overcrossings, and this acts on x tensor x tensor x. But every time I switch two factors x, I just get a factor q. So I just get q, how often? Well, the length of sigma, meaning the number of neighboring transpositions I need in a reduced expression to write sigma. So it's somehow this combinatorial quantity, right? Some polynomial in q that I multiply with. That's all that happens. And then there is this very nice formula, maybe people know from invariant theory, from reflection groups. You can, this polynomial can be written like this. So it can be factorized into products of this form. And now you exactly see when is this element, I mean, that's the only element you have in degree k, when is this element in the kernel of the quantum symmetrizer? Well, it's exactly if one of these factors is 0. And this is exactly the case if, well, q to the k or some smaller I is the order of q. So this quantity is non-zero, 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 until for the first time for I equals k, q to the k is equal to 1. And then for higher k, sort of one of the previous factors, I mean, there's more factors, right? Gets 0. So this factor is something, 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 until at some point it's 0, 0, 0, 0, 0, because some of the factors in the product get 0. And that's exactly what you see, right? And it cannot be q equals 1 because that's exactly the one factor that is not there. And explicitly, if you do this for S3, as we did before, we have one overcrossing, two overcrossings, and this funny 3 overcrossings at the end, which we had. And altogether, this polynomial can be factorized to this times this, which is exactly this statement. And you see that if q is -1, or if q is a primitive third root of unity, then x cubed is 0. So x cubed is 0 if either sort of already x squared is 0, or if sort of x cubed is the first thing that is 0. Right? I think this is a very important example. And on the categorical side, what you could do is you can say, well, this is a Hopf algebra. Can we divide stuff out? Well, we can divide stuff out only if some power is a primitive element. And you can see that this condition exactly means that x to the L is a primitive element. So you can divide it out. And it's a quotient Hopf algebra. So this condition is equivalent to the fact that x to the L is primitive Hopf algebra. So it has coproduct 1 tensor x to the L plus x to the L tensor 1. So that's the Hopf algebra interpretation of what we're doing. Now let's look in rank 2. So suppose we have 2 basis vectors. What we can do is we can look whether we have a quadratic relation. And you do this by, we have this very, very easy quantum symmetrizer that was simply, how can I draw here? Here. So remember that the quantum symmetrizer in level 2 was 1, plus the braiding. So what is in the kernel of this? Well, maybe some combination of xi, xj with xj, xi. So can we make this 0? Well, and the fact is, what we claim is we can do this exactly for this linear combination if qij, qji is 1. So if the braiding is symmetric. So in particular, if we have a braiding which is always +1, so it's the usual trivial braiding, then we get a symmetric algebra because commutators are 0. And if it's -1, then anti-commutators are 0 because of the previous slides, squares are 0. So it's the exterior algebra. So somehow the moral of this, I would say, is suppose you want to define Q commutative algebra, Q polynomial ring. At some point you say, I want the relation xi, xj minus qij, xj, xi is 0. Well, this is fine. I can want this. But now, of course, I want the same relation for j and I switched. And these two relations are usually not compatible. I mean, they're only compatible if qij, qji is 1. If I choose qij anything and qji anything else, then I cannot impose these two relations at the same time. So somehow the Nichols algebra somehow has as many relations as possible. So if this relation is possible, it has it. And if it's not possible because qij, qji is not 1, it does not have this relation simply. It's maybe closer to a free algebra, but maybe there's coincidences higher up. And if there is, then there is relations at this level. And if there is no coincidences, if qij is somehow a generic bunch of numbers, then it's simply the free algebra. So somehow it wants to have as many relations as it can. Maybe that's a very informal way of saying. So one of these higher cases that can happen is if now qij, qji is not 1, so it's not a symmetric braiding, but it is a power of qii, so of the braiding I has with itself, for some number a, then one can check that this is maybe not 0, but the iterated braided commutator is 0. This should be a little q, sorry. So somehow this quantity, which seems, I mean, I once had the fun of writing down, I mean, you can inductively sort of write down what the factors are and so on, and it checks out. But somehow the idea is just, it's how it is. I mean, if you have this relation, this is one of many things that can happen. If you have this coincidence, then the Q commutators that you iterate are in the kernel of this quantum symmetrizer, and then this is 0. But this is exactly what we have as a set relation. So you already see if the braiding has a certain relation. Remember that we had in this Lie algebra case, we had qij is q to the alpha I, alpha j. Then this relation exactly says that A is the Cartan entry. So somehow the Nichols algebra produces by itself quantum set relations. And maybe that's one of the powers of the construction. You don't have to put them in. It's not like in quantum groups where you define the quantum set relations. It's more like you just say you have a certain braiding that comes from, maybe in this case, the geometry, and the braiding somehow by itself produces the quantum set relations. And that's a very surprising thing. I think this was not expected at the beginning. At the beginning, I think it was more descriptive. I mean, you had quantum groups in mind and you try to find this, and then several people, Lustig, Voronovich, and so on, noticed that somehow there's universal properties that somehow force the quantum set relations to hold, even though you don't put them in. And this is, I think, very surprising. So, is there any questions to these examples? I think maybe we should have them a little bit in mind. So now what do we have? So what we have is a bunch of very general theorems now. So doing examples is nice, but what we actually have is we have a root system theory in general. So if you have suitable Nichols algebras, which assume to make some finiteness conditions, they don't have to be finite dimensional, but they somehow, all the stuff you can do, all the actions and so on have to be finite. So if you have suitable conditions, then what you can prove is if you compute the Nichols algebra of some object with some braiding here, 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 so of a direct sum of objects, then the Nichols algebra of this whole bunch is, of course, not going to be the Nichols algebra of these components, because those will not commute in general. But somehow you will have pieces from the Nichols algebra of this object, and so on. And then a Nichols algebra of something involving commutators of maybe alpha 1 and alpha 2 object, and so on and so on. And that's, and again, the Nichols algebra of this. And somehow at some point you're finished. This can be finite, it can be infinite or so, but somehow this gives you something like a PBW basis. And so the statement is that this is an isomorphism of objects in the category respecting the grading, but not an algebra. Of course, the algebra structure is here some commutators, right? And for example, if the braiding between alpha 1 and alpha 2 is symmetric, then the Nichols algebra of the direct sum is the tensor product of the two Nicholsons. But if it's not so, then you have higher stuff, right? So there could be here some b of x alpha 1, alpha 1 2 maybe I should write or so. So where there is the commutator x1 x2 is non-zero, but maybe the commutator of x1 x2 with x2 is 0. So at some point maybe terminates, or maybe it's an infinite bunch, could also be, but this sort of structure you have. And that is of course something you are very used from the PBW basis of a universal enveloping of a Lie algebra or a quantum group. Diagonal Nichols algebras, which are finite dimensional, were classified by Heckenberger. I think this is a very great result. In this case, all these objects in this category here are simply one-dimensional vector spaces, and they have some braiding Qij between them. And what you have is a tensor product decomposition into truncated polynomial rings of some x alpha, where alpha starts to be 1, 2, 3, 4, and so on, and then goes over composites like commutator 1, 2, and maybe 1, 3, and so on. So somehow you have here for each root you have a higher commutator. Like, let's look at how UQSL3 positive part would look like, where you have an x1, you have an x2, then you have a commutator x1, x2, and then nothing more. So this commutes with this, map to braid commutes with this, and this commutes with this, and that's it. So in this case, the root system would be, you have an alpha 1, you have an alpha 2, and you have an alpha 1 plus alpha 2, and that's it. And I think it's very surprising that this Nichols algebra by itself sort of comes with a notion of a root system. And actually, the root systems you encounter are not always the common ones. So maybe that's an important lesson to be learned. They are a little bit more generalized, but they still behave quite nicely. And in which way generalized? So now I try to focus solely on the root system theory you get without looking at the elements and the relations. So the root systems very roughly look as follows. So you have, like for usual root systems, you have an arrangement of hyperplanes intersecting the origin. So there's some hyperplanes. But if you remember, for a Lie algebra, you always have, I mean, each chamber, each simplex that you get by intersecting all these hyperplanes looks sort of roughly the same. You have a Weyl group acting on them by reflection, and each side of this thing looks the same. It looks like a Platonic solid, maybe. And in this case now, they're slightly generalized, so we don't have to get a Platonic solid, but something Archimedean, right? You have different sides that can look different. You have a Weyl chamber here that looks like a equilateral triangle, and you have a Weyl chamber here that looks like a right triangle. So technically what happens is it is not anymore in a Euclidean vector space. So reflections are not defined by an orthogonal reflection, but it's more like they're defined by arbitrary linear maps which have to be compatible still in some sense. So somehow you drop the condition that everything comes from a Euclidean structure. And that's why this is allowed. So here you have nice linear maps that map this triangle to this triangle and this triangle to this triangle, but they are not sort of.
I have a question.
Please.
So I understand that that you don't have reflections anymore, correct?
Not orthogonal reflections, just linear maps.
Yes. So are you aware? So can you define like simple systems, and are you aware that Serganov and Penkov have defined a theory of virtual reflections? I mean, do you know this?
That's exactly the comment I would have made at the point here. You're very right. No, you're very right. The point is, so you know this from super Lie algebras. So somehow for super Lie algebras, and also, which we discussed before, for Lie algebras in characteristic P, because there's also a theory there where you have problems. In both cases, people noticed that you have some little bit generalized root system theory. So you have like usual reflections that respect the scalar product, but you have also odd reflections on odd roots in the super Lie algebra case, which somehow seem to disturb everything. And those are exactly in this picture the reflections that go maybe from a right triangle to an equilateral triangle. So somehow and I think this is a very good thing that we can pull out of this theory, that we have these special cases. And so for example, this example I have comes from a super Lie algebra. So it exactly would be one of these works that you just cited.
I ask a question, because I'm doing work with Dimitrov on Serganov idea and so on, and we are looking at the generalized root system exactly the way you're saying. So are you getting something that is beyond, you know, the super algebras and Lie algebras? And if yes, what are you getting? Because we are getting a lot. So I'm asking.
Yes, indeed, that's exactly the point. So there is this classification. So Nichols algebras before were really interesting and difficult, and this root system theory by Heckenberger, Andruszkiewicz, Schneider.
Yes.
So starting in the diagonal case by Heckenberger, and then going into more semi-simple cases with I will have some examples later, and then this Heckenberger-Kunz work is somehow trying to look at root systems sort of by themselves without the Nichols algebra sort of being part of it, and so they axiomatized. I mean, it was axiomatized before. I think Yamamoto Eckenberger, I think, is the reference. But then they somehow noticed that so you can axiomatize what means to be a generalized root system, and basically it is really an arrangement of hyperplanes and linear maps that somehow do what the reflection should do, except there is no scalar product they respect. And then you want it to be crystallographic. So you want that in each base, so for every Wald chamber, you have a base of simple roots and normal vectors of this choice of normal vectors.
So my question is, these systems, do they look like a projection of systems in other, in Lie algebras, the super algebras? Because this is what Dimitrov and I have been doing, projections.
Yes.
Okay.
So the one is Heckenberger-Kunz did a classification. So there is this classification, which basically says that there is a couple series that looks like D21 alpha, and then there is many more exceptional cases. I forgot, maybe 80 or something. So there is many more exceptional cases up to rank 8, and then that's it. And there is an infinite family in rank 2. So you have a classification of all.
We think too. We don't have a proof for our system, but that's what we think too. So it is compatible, yes.
And then there is some work I did with Kunz at some point where we say, given a root system and you have some hyperplane and you project down to the hyperplane, you get another root system, because that's something you do very often in the Nichols algebra proofs. Yes. And the root system, that's probably something you're also interested in. So maybe we will do this at the very end, but very interesting that you encounter this at some places. So yes, there is this, and that's also, by the way, the reason why there is no exceptions beyond E8. So somehow all the exceptions you get from restricting down from E8 and E7 and so on. So there is no somehow except for this rank 2 cases and a couple of rank 3 cases, everything comes from sort of projections from root systems. And that's, I think, also very interesting that this is the case.
I have a question. This rank 2 system does it correspond to the spheral cuts, Lie algebras characteristic 2, or is this brown guys?
Well, rank 2 there is an infinite family. So rank 2 there is a family defined by triangulations of n-gons. So there is an infinite family of examples. But yes, I mean, some of these root systems you know from super Lie algebras. Some of these root systems you know from Lie algebras in characteristic P. Some of these root systems you know from super Lie algebras in characteristic P. And some of them you don't get from any of these. But but maybe it's not so, I mean, it's a little bit mysterious, but maybe it's not so mysterious if you think that just there is more primes interacting. So if I say superly algebraic characteristic P, it means the prime 2 is special and the prime P is special. But now what do you do if there is 3 and 7? And we don't have a good name for that. I mean, it's like a 3-Lie algebra in characteristic 7, but nobody looked at this ever, I think. But probably somehow that's the spirit. But those are the 2 boundary cases that were known before. So this, I think this is another level of generality, right? I try to sort it a little bit like there is this explicit things you want to know, finite dimensional Nichols algebras, but now you have this generalized root system theory. And I think that this is a very important and fundamental definition, this generalized root system. And as I said, I think the surprising thing is you can classify it. I mean, you would think this is an arbitrary thing, right? An arbitrary bunch of linear maps that somehow switch sides of hyperplanes, but they are so restrictive that you basically get Lie stuff back. I think that's a surprising thing that you can even classify them. More questions? I think this is very nice that we have interactions. I missed this in the last 2 semesters where we only had online talks. In online talks, usually nobody says anything, and I think it's very nice that this is different. Even though we're not in presence, but somehow. So maybe if there is no more questions on these other cases, let's say another type of examples that are a little bit more complicated. So if you have a finite group, not necessarily abelian anymore, then there is a braided tensor category, which are GG Jeter-Drinfeld modules. So those are G graded vector spaces with a G action with the following compatibility. If you digest this definition long enough, it's actually not so hard to see that the simple objects are parameterized by a conjugacy class, right? Because you need, if you have a degree, you need to have all the conjugate degrees. So the conjugacy class, and then you still have some open parameter. You can choose an action of the centralizer of H, which is exactly the stuff that fixes VH. You can choose an irreducible representation of this, and this together glues together exactly to a simple object. So this is a non-trivial example of a braided tensor category, because you have a braiding if something in degree G and something in degree H gets switched. Somehow the G acts on this H, and you have to know what act means, so there has to be a G action. So somehow if you switch stuff, it's not just a scalar, but it's like an action of the degree on the other element. So that's a little bit the generalization beyond just having Qij numbers. So for example, for the symmetric group S3 over the complex field, you have the conjugacy class 1 with 3 different irreducible representations of S3, 1, 1, and 2-dimensional. And then you can have the conjugacy class of 1, 2, or the centralizer is Z2, so you can choose a Z2 action here still. So those are there's 3 conjugate layers, 1, 2, 2, 3, and 1, 3. And then the same is for 1, 2, 3. So it's a 2-dimensional, and you have an action of Z3. So there is 2, depending on how your centralizer acts by 1, by a third order of unity, or by another third order of unity. And now the question is, so that now maybe for this, we more see how these questions for Nichols algebra separate into 2 different questions. So the first question is for an irreducible object in this category. So this is a big guy, but it's irreducible. What is the Nichols algebra? So this is a difficult question. This is a very non-trivial question. For example, if you take the transposition in S3 with -1 action of the centralizer, so this is some 3-dimensional representation with some non-diagonal braiding, then the Nichols algebra is dimension 12. Namely, it starts with the identity, so degree 0. Then there is 3 elements, because this is a 3-dimensional space. Then there is 4 commutators. They form something like this. And then there is 3 commutators of degree 2. And then there is 1 highest element. And you see very nicely, so this is 12, right? So this is the graded dimension. And you see very nicely that there's a Poincaré duality, which you can prove in any case you have. So this is another thing that you have for Hopf algebras in general. So you have this sort of Poincaré duality in the graded components. And so at this point, we have not used any root system theory. I mean, there is tricks. You can look at sub-configurations, and then you have root systems. But sort of, in principle, this thing does not have a root system-y thing. The root system comes into play if you now take direct sums of several of these guys. And then the root system exactly measures sort of which compositions of these, which commutators between the different irreducibles are still in the picture. So somehow you have this theorem, which we had a couple of slides ago. So somehow you can express, using the root system, exactly expresses this Nichols algebras in terms of this Nichols algebra, this Nichols algebra, this Nichols algebra, and then maybe some composite Nichols algebra for these two guys, and then for these two, and so on. And at some point it terminates or it doesn't. So that's somehow you should think of a root as a combination of these different irreducibles, so some braided commutator between these different irreducibles. And you see that now a root can be a very difficult thing. Before you had for every root just a truncated polynomial ring in one variable. So B of like one of these one-dimensional guys was basically just polynomials in X divided by some power. That was the Nichols algebra of the one-dimensional space, because those are the simple constituents in these examples. It's in diagonal case. And then the Nichols algebra of x1, x2, so the span of x1, x2, and so on, is then something with the roots, right? But here, already these guys are very non-trivial. They can be arbitrarily large. So somehow in each root, there is a big Nichols algebra associated to this simple object. And then the root system tells you sort of how many of them you encounter if you take a direct sum of things, the simple root. So to each simple root, one of these would be associated, and to each composite root, some combination of them. And it's a very non-trivial question to find all finite dimensional Nichols algebras of this type and to find out what their graded dimension is and so on. This is still open, but mostly solved now, but there's still open things. Especially this is a very difficult question, and this question can be solved with root system theory. That's a little bit how they play together. And I've made this poster at some point, which you can find on Wikipedia, which shows you all examples that are known so far. So, the diagonal case, where for every root, so I'm depicting a root which is a one-dimensional space by one dot. So here you have root systems built up of one-dimensional Nichols algebra spaces, right? And one-dimensional Nichols algebras of one-dimensional elements. But now if you start to go to, so here, for example, for S3, you have this Nichols algebra of dimension 12, which is associated to one irreducible object. So that's actually A1. That's the root system of type A1, but it's like a fat point. There is a non-trivial stuff going on in this one A1. And now the question of root system theory is, how can you compose them to non-trivial Nichols algebras that are larger? And so my contribution to that question, which I want to talk about in the last part, is how to construct a large family of those. So people have found a couple of examples by certain explicit constructions. So one Coxeter groups in particular by Belinsky-Schneider. And then many examples of like simples, so rank 1, but with some very non-trivial thing going on. And those examples can be constructed completely sort of uniformly, I mean, using Lie theory again. And that's what I want to talk to you about. Again, as I say, you can find this on Wikipedia, and I put all the cases that people found here. Classification for the abelian case, so for one-dimensional stuff, diagonal braidings, is finished by Heckenberger. And in the non-diagonal case for a group, curiously, we know everything by work of Heckenberger and Vendramin, we know everything in rank 2 and higher. Basically because the root system theory is so strong that it determines what can happen. But in rank 1, we don't know. And compare this, I mean, in rank 1, there can be anything in a point. It's very difficult to see what the Nichols algebra is. So let's see how this construction works. So the input of the construction is called the folding construction. So the input of the construction is the following. Let's start with some Drinfeld module, so over some group gamma, so a gamma graded gamma module. And now we want to make gamma a little bit larger. So imagine gamma to be abelian. So now we have a group Z, imagine a cyclic group like Z2, acting on this X, and some central extension of gamma, which is then maybe a non-abelian group, with some associated cocycle. So this is my date, and this action should respect the gamma grading, but it should not respect the gamma action. It should be somehow almost able to respect the gamma action, meaning that if some g in gamma acts, and afterwards I act with this z, it's the same as doing it the other way around, but there is the co-cycle of g and h appearing. So this is an action of a group Z, we get a Drinfeld module, which is somehow not completely respecting the gamma action, but up to a 2 co-cycle sigma. And from this we can define a Drinfeld module over G, which basically looks, we take X as a vector space, we pull back the G action, so this new group Z acts trivially, but the G co-action is defined as follows. You decompose into eigenspaces by theta, by this action of Z, and to each eigenvalue, an eigenvalue is in Z star, it's an element in Z star, it's a character on Z, right? Eigenvalues of Z acting, you have a different pre-image in G. So you say that this is the degree. So the new degree is composed of the old degree plus the eigenvalue of this new Z. And what happens in this way is, because the action will permute sort of different irreducibles, they merge together to one orbit. And that's exactly what happens in a Drinfeld module, because the larger group, several elements are conjugate, which before were not conjugate. So that's somehow stuff that was before small and sort of disjoint, like A2 or so, can be merged together to a bigger irreducible representation, sort of an irreducible object in the larger Nichols algebra. And let's take very briefly how this looks in examples. So for example, Z2 cross Z2, we can extend to D4. And now let's take the following Nichols algebra. So that's UQSL3 cross UQSL3 with an action interchanging these two. This is a very trivial way of constructing an action, right? You just make 2 copies and you have to put the action. I mean, here I denote somehow how X and Y act, some characters. You have to put the action in the right way such that this twisted condition I said is true. So that this exactly comes with a co-cycle here. And then if you fold this, what you get is a new Drinfeld module, which now has a 2-dimensional conjugacy class here and a 2-dimensional conjugacy class here. And those are exactly the 2 conjugacy classes in D4, right? And that's how, so maybe that was too fast now, but that's how really, if you work it out, how you can very explicitly say what the new Nichols algebra in the Drinfeld module is. And now it's sort of SL3, but SL3 with fat points in the sense of, for the one root, there's a 2-dimensional guy, for the other root, there's a 2-dimensional guy, and for the third root, alpha 1 plus alpha 2 here, there is sort of a third 2-dimensional thing. So that again, together, it's 2 times 2 times 2 dimension. Let's say, sorry, it's so depending on what the root is, the dimension here. So maybe it's an Lth root of unity. Then the dimension here is L cube for this UQSL3 and L cube here. So it's L to the 6. And here it's still L to the 6, but it's sort of L to the square for this Nichols algebra, L to the square for this, and L to the square for the root 1, 2. So somehow that's what happens. And we can have more complicated examples like with a branch point. So also these can be folded. And you see, you find exactly all, so you find many high rank examples of Nichols algebra with non-trivial conjugacy classes here. And in fact, what turns out by this Heckenberger and Vendramin result is that all the large rank Nichols algebras that you get, which are finite dimensional, are of this type. Just in small rank, you have some exceptions which are not of this type. But in the large rank, they are all folding. Somehow there's again more Lie theory than you thought. Yes, was a question?
Yes, so you can hear me great. Okay, so I see a lot of resemblance within these diagrams and what the Borel, the Siebenthal paper by Constant. I don't know if you took a look at it. It's a very interesting paper where he constructs generalized root systems by taking roots and not respect to Cartan subalgebra, which is a maximal toral, but to a non-maximal toral subalgebra, so that the root spaces are not one-dimensional, but are more than just one dimension. You get diagrams similar to the ones that you construct. He doesn't do it. Me and Dimitrov do them in our paper, but did you know that constant looked exact? No, you didn't. Okay, sorry. Okay.
No, tell me the quote again. Constant and?
So constant is called, is a paper with the title that has Borel de Siebenthal into it. The word, the Theorem of Borel de Siebenthal, because a special case is to look at real forms, but really it is a very deceiving title, I must say. Okay.
Yes, no, you're exactly right. So if you think about Satake diagrams and real forms, that's exactly where you have the resemblance.
Of course, I know it's right.
Yes. Sure. So I mean, the Satake diagrams is a sort of it's of course something evident you have here, but you will see that we get more of this actually. So this is the folding thing, and the funny thing is this is an old story actually now for me. This is how you can construct all these large rank things. And now let's I want to a little bit tell you, maybe let's take some remarks. So first of all, these twisted automorphisms do not preserve the braiding, but they preserve exactly what you need to have for the Nichols algebra. They preserve double braidings and self braidings. So somehow they are automorphism of the essential part of the Nichols algebra, or of the quantum group if you want, but it does not exactly preserve the braiding. This is exactly the point. And the algebra you get as an algebra is somehow the same Nichols algebra, but the root system is, as we said, folded. It's a different root system. It's F4 if you start with E6, in the same way as in Satake diagrams, for example. And the coaction is now sort of enhanced. I mean, from a gamma coaction to a G coaction. So now it's a larger group acting, somehow incorporating the symmetry group. You extend by the symmetry group. And you can also do this if you have something very similar appears, and we notice later if you have abelian groups with non-trivial associator, because basically projective representations have to be higher dimensional, and it's exactly the same. Basically, because projective representations, if you centrally extend them, then they become usual representations. So if you try to do like quantum groups with projective representations and so on, you get similar stuff. Yeah, so maybe that's all not so incredibly important. So what I want a little bit maybe say is there is different pictures to look at this. So the one I gave you was the one most directed to really construct Nichols algebras over groups, because that was a big question at that time, and I think it still is. But since the works of Heckenberg and Benjamin, I think many things are now known. But sort of one picture you can have in mind is much more algebraic. So you can take the Nichols algebra together with the group ring, and then what the construction actually does, it makes the group ring larger, and the same Nichols algebra, but now over this group. So it's some smash product. And how you do this is basically you sum over this Hopf algebra and some twists of it, twists in the literal sense. And you see what happens on the level of the group ring is exactly you take the group ring gamma and then some twisted group rings, and the direct sum of twisted group rings gives you again a group ring of a central extension. So that's sure cover theory. And that's somehow the essence of what we're doing. I mean, I spelled it out for the Nichols algebra, but basically what we're doing is have a Hopf algebra and some twists of the Hopf algebra. You add it all together, you get a new Hopf algebra, which is larger. And here, in some sense, only the group gets larger, but the Nichols algebra somehow goes along the way and becomes now over the larger group. And the categorical picture of this is if you have a homomorphism from Z to the Bra-Picard group, then there is this famous work by Ettinghoff, Nichols, Ostlik, how you have extensions of tensor categories, and that's exactly what happens here. So it's a specific, quite non-trivial instance of sort of a general picture that you abstractly expect for a tensor category somehow. And the nice thing here is you can have more complicated things. You can there can be more complicated Hopf algebras than just group ring times Nichols algebras, and still the theory works. But maybe that's again more for the specialists. So because there was so much, yes, let's maybe talk about this, even though it's not completely related, but it's exactly the question you had previously. And I knew this, of course, from the contact that this may be something that you might like. So there is some different work at the first sight. Which is as follows. Suppose you have a Nichols algebra over some object, and you have some sub-object here, it can be a direct summand, by, then what you can do is Bx becomes a Nichols algebra over the Hopf algebra By. So this is like a relative situation. So you have a Nichols algebra over one big object and over a small object, and the Nichols algebra over the big object becomes a Nichols algebra over the smaller object. To be precisely the coinvariance. If you take the coinvariance, they become a Nichols algebra over the smaller object, and you can even say by which Drinfeld module. So this is like the adjoint action, basically. So this is a very important for this whole root system theory, something that is sort of standard in this theory now. Basically, if you construct a reflection operator in the most general sense, what you do is you take the subspace, the reducible subspace that belongs to one root, you look at the whole Nichols algebra over the subspace, and then you somehow dualize the subspace Nichols algebra and glue it back in. So that's how the most general sort of reflection theory really hands-on looks like on the algebra. So that's this relative situation is something that people have looked in particular if the smaller thing is one root. I mean, it's the Nichols algebra generated by one root, which can be arbitrarily large in the general case, but it's a truncated polynomial ring in the usual, in the diagonal case. And now what was just an interesting question was, what is now the root system of this as a Nichols algebra over this? And for example, if you have SL3 over SL2, what happens is exactly this. So you have the root alpha 1 and the root alpha 2 and the root alpha 1 plus alpha 2. And now let's take, so this is a whole Nichols algebra, that's UQSL3, the positive part of UQSL3. And this is the smaller algebra, that's UQSL2. And how does this act with the adjoint action? This becomes a two-dimensional module. And now this is a Jeter-Drinfeld module over this. And the Nichols algebra of this is exactly the co-invariance of the big Nichols algebra with respect to a small one. So it's the rest, so to speak. So for example, and this is of course a very simple picture. So but in this case, this Drinfeld module, as it says here, is exactly these two together as a Drinfeld module with the adjoint action of this one root sort of playing back and forth. And now you can interpret this behavior. What does this do for arrangements? So what it does is basically you have the hyperplanes, the roots for the big Nichols algebra, and you have some subspace. And now you restrict. So now you intersect all your roots with this subspace, and you get a new root system. But the new root system is not necessarily any more of a lead type, right? It can be something much more general. And this is exactly, and at this time we didn't notice that so much, but when we started to finish this paper, we noticed that basically the folding procedure and this parabolic restriction procedure are actually two sides of the same thing, and we don't really understand exactly what the general theory would be, but there should be something like a mixture between these two. You should have, like for Satake diagrams, right? You have automorphisms switching Dinkin diagram nodes, and you have parabolic restrictions, right? Things that are sent to minus themselves. And then somehow the general case is like a mixture of these two. And that would be very interesting to see this. And if you see this in examples, the funny thing is it produces many Nichols algebras over root systems over which we don't know diagonal Nichols algebras. I mean, basically all root systems you get this way, at least all in rank 3 and larger. So for example, and this is something where you again see why it's, as you already pointed out, why you see it's necessary to have this generalized root systems. Let's take E7, and let's take this sub A1, A1, A2, this sub Nichols algebra. Then this becomes a rank 3. So if you collect all the roots that you get from a joint action here and here and here, it's a rank 3 Drinfeld module over A1, A1, A2. But this will not be a standard root. So this is just simple roots, but it will not be a standard root system. There is many more roots than you would think from this picture. And you see this because if you start reflecting, this picture does not stay invariant. So you go to a different selection of black points. And that's why you sort of switch your Weyl chamber. Your Weyl chamber will look different. After some reflections, suddenly your black point is here, and then you have a very different data.
I am sorry. So I need help to visualize your diagram because we write the diagrams that are the same. So here the parabolic is when you choose the black dots, yes or no? The parabolic that you look at.
Yes, the parabolic is here the black dots.
Yes, so the root system generalized, it is obtained by looking at the toral subalgebra. That is, you decompose with respect the toral subalgebra that, you know, the parabolic splits into Levy component and then nilpotent, right? And then the Levy component is the centralizer of the toral subalgebra. That is the toral subalgebra that you use to obtain the root system at the orthronic. Are you aware? This is theory of constant.
Yes, no, I will have a look at this. No, I'm not aware of this. So I think this is very interesting. So,
Yeah.
so I'm just saying, so from what I know, the point is that you get a root system in this way, but you can see it's not a standard root system. It's not the one where all wild chambers are the same, because you see. And what we checked was merely, first of all, that you obtain root systems. I mean, we have Nichols algebras for this root system.
Yes. No, but it's worked by Constant, not me. Constant. Okay, this is exactly that. Yeah.
No, this is a very interesting suggestion, of course. So I mean, judging from the Satterger diagram, you would think that this appears at places. So the reason for us for doing that was merely to see root systems of these relative Nichols algebras, and to see that in this way we can produce Nichols algebras which have root systems which before we did not see. So there is a list of root systems that you get for diagonal Nichols algebras and for non-abelian groups, but they don't cover all the root systems that there are. The classification. But now, apart from some small examples in small rank, now they cover all. So every root system can be realized by a Nichols algebra, but not necessarily diagonal or group, but these relative Nichols algebras.
But are they coming all through Dinkin diagrams? They're all coming by putting black dots in Dinkin diagrams? I see.
Except rank 2 and a couple examples in rank 3.
Okay, thank you.
Yes, and that's also, by the way, that's the funny thing. After we did this, I mean, in Kunz, Michael Kunz was, of course, one doing the classification before we did this. So after we did this, we noticed that, of course, it's very fun. All the exceptions that you get in the classification are below rank 8. And that is no coincidence, because they all come from projecting down or restricting from E6, E7, E8, right? That's exactly what happens. Yeah. In the generic case, if you restrict, you just get another of these families.
I see.
Mm-hmm. So that's maybe something for me. It's not disjoint, but a separate direction. And I would like at some point to have sort of a common generalizations of these two things, of this folding by automorphism and this parabolic restriction, which both I think we understand, but we don't know how this generalizes together. And that's what I want to say basically. And let me maybe just point out. I will not go into detail with that, but let me just point out with this slide. That what I'm working on right now, what I find very interesting is that there is certain integrals. So those are complex integrals in n variables. So there is here variables z1, z2, and so on, zn. And I'm looking at this function. So this is a complex function with some parameters mi and mij. And this is a multi-valued function in n variables. And I can try to integrate them over circles. So, but over circles, of course, in a multi-valued function, those are fractions maybe. It's difficult, so you have to lift and then you integrate over a spiral, right? It's not a circle anymore. It lifts in the multi-valued cover to some path. You take this integral. It converges under some assumptions, which are not important, so that have to be too large. And the point is that you can ask which linear combinations between these hold. And the point is this linear combination is exactly 0 if the respective element in the Nichols algebra is 0, where you take as a braided vector space just an n-dimensional vector space, and as a qij, you take e to the pi I mij, which is exactly, it's -1 to the mij if you want, but mij is fractional valued, which is exactly the monodromy, the non, you know what I mean, the non-single valuedness of this function here. If you take an analytic continuation, you get exactly this -1 to the mij. So this tells you that Nichols algebras appear in this. So if you do this for small cases, you get some hypergeometric functions. So you see that Nichols algebras also appear as the structure constants, if you want, of these integrals. And the motivation for how we got to this is that you have certain applications in physics where you have certain models of conformal field theory. And the conjecture is, this is the Kashtan-Lustig conjecture, a logarithmic Kashtan-Lustig conjecture. The conjecture is that the representation theory of these conformal field theories is somehow characterized by Nichols algebras, by quantum groups, but sort of my understanding, the ability to generalize to Nichols algebras, and it does. So Semikhatov and Tipunin had some ideas of doing this with diagonal Nichols algebras already, and so what I've basically proven is that you can see that exactly these integrals that appear on the conformal field theory side are 0 if the Nichols algebra has a relation, simply again because of this Matsumoto stuff, right? I mean, you still have a braid, you have like braid group acting here on all these monodromies around these poles. Somehow we go very much back to how quantum groups were originally defined by monodromies of physical systems somehow, if I don't know how to say this. And of course, we can also now try to ask what folding means here. I think I know this. So there's more complicated physical theories that have G acting and so on and so on. So that's just another point where I want to say Nichols algebras should be important, and they appear not just quantum groups, but arbitrary Nichols algebras appear as very natural structures. Basically, if you do this for integral value stuff, you get Lie algebras. So that's a theorem in physics. I mean, not a theorem, but like a principle in physics. Whenever you do this, you usually get Lie algebras. But if you take fraction values here and non-single valued functions, you get Nichols algebras instead. The braiding exactly measuring the non-single valuedness and the monodromies around the poles. So that's just maybe to conclude and to get back to this analysis picture that actually quantum groups started at. So yes, thanks very much for the attention. And of course, you can have more questions if you want.
Okay, well, thank you very much for a very interesting talk. Very nice. So there are questions from the audience. Well, I think there are enough, but are there questions from, let me just.
I was molesting the speaker. I don't want to ask more.
So if not, I'm going to ask a naive question, because we're quite interested in the Nichols algebras that we found that are coming from the Grassmannians. So if you took this procedure of crossing nodes and you just crossed a single node on the A series thinking diagram, what does the corresponding Nichols algebra look like?
Well, the Nichols algebra, I mean, this is exactly what happens. So the Nichols algebra, so you have, let's say you have A3, right?
Right, yeah. Crossing node.
And I have these nodes, right? I have maybe 1, 2, 2, 3, and 1, 2, 3. And now if I cross out this node, it means I have a UQSL2 basically standing here. And then this becomes a module. This becomes a module. And the commutator of these two elements becomes this Nichols algebra module. So what you will have is B of so the co-invariance, so B of, let's maybe just write A3, and the co-invariance under B of A1, let's just write it like that, is basically exactly B of something two-dimensional plus something two-dimensional. So that's this and this. And if you do the root system decomposition, this Nichols algebra has a A2 root system in this generalized sense. So it's now B of something two-dimensional. This is the first root. B of something two-dimensional. This is the second new root. This is a tensor, yes. Tensor. And B of something one-dimensional. And this is somehow the new root alpha 1 tilde, the new root alpha 2 tilde, and the new root alpha 1 plus alpha 2 tilde, right? So that's how the Nichols algebra looks like. I mean, it's simply the co-invariance. Is you have a Hopf algebra and a sub-Hopf algebra, and you have a projection, and you just take the co-invariance with respect to this projection.
Okay. Thank you. Thank you very much.
I have a bit of naive question, because probably the answer will be too hard, but suppose I have some braiding just given written on the paper. Is it any chance to determine that this braiding is given by Dieter-Drinfeld braiding for some group? Because, or even maybe a more simpler question, we have some Hopf algebra which is complicated and finite dimensional, and we have a Dieter-Drinfeld module for this Hopf algebra. And we consider Nichols algebra, but also we know that this Nichols algebra will be constructed could be get from the Dieter-Drinfeld module over some group algebra. So is it easier to see such a correspondence?
So first of all, I would say the answer here is definitely no, because it's just not true. I mean, most braidings are not. I mean, you can of course say that when braidings are diagonal, I mean, you have to find a diagonal basis, which also computationally is of course hard. But I mean, this is clear. And for a group, I think it's no, so I wouldn't know any answer. So of course you can easily write down braidings that are not of group type.
Yes.
Actually, already the ones I wrote down with parabolic restriction are not of group type anymore. I mean, they are more complicated. They are over some other algebras. So because that's how we get new root systems. I mean, otherwise we wouldn't get new root systems. So many are not over this type. But of course, and that's the funny thing about the definition. So as a Hopf algebra, of course, the Rindfeld module is important. But as an algebra, to know the Nichols algebra and to know the root system, it's only important to know sort of how this decomposes. I mean, somehow the structure of this as a braided vector space is enough. It just depends on the braiding.
Yeah.
So if you have a simpler model for the same Rindfeld module, of course you can compute the Nichols algebra. Is that the question?
More or less, I could just specify to the case of the papers that I sent to you that as one of the surprises from your comments that we started from a Rindfeld module over quantized coordinate algebra. And so this Rindfeld module is reducible. We constructed this Nichols algebra, and it turns out that it's the Nichols algebra is the same as a parabolic restriction of something of a group type. So maybe only maybe in the case of quantum groups only, I would like to see, is it possible to pass from one to another easily? So because to start, I don't know, from some representation of UQ of G and then turn it to some Rindfeld module over some group, maybe while group, and consider some parabolic restrictions. Yeah, to play in this with these things.
So what I definitely think is, and there was actually also one aim of this paper with Michael Kunz. So suppose we have a complicated braiding, like a Rindfeld module over a quantum group. How can we compute the Nichols algebra? It's extremely complicated, right? But it's interesting for several applications. So the idea was basically somehow to reverse the whole thing. So suppose I find a larger quantum group such that I have a how should I say? So I have UQG acting on some X, and I want to know what the Nichols algebra of X is. And now suppose I find a UQ larger G such that X is this more or less G over G, or I don't know how to write it, right? This is coinvariance.
Yeah.
Then I know what it is. Namely, it is the coinvariance.
I see.
So that's somehow how I wanna see this. So it's a way to produce sort of Nichols algebras, because there's sort of a larger quantum group behind it. I do not know whether there is other cases. So I would of course assume there is, but I wouldn't know how to compute them. So you can probably write down an X over UQG, which has a finite dimensional Nichols algebra, but it's not of this form. But I wouldn't know an example.
Okay.
So of course you can write down anything and you get some infinite dimensional B of X, but all the finite dimensional cases, so far I know, but that's not it's just a statement about my knowledge. All the finite dimensional examples that I know come from this construction. So they come from parabolic restriction of something larger.
And is there am I right that now you were speaking about the Lussig small quantum groups? So any connection with this bigger one, the Rindfeld one?
Well, how should I say? Not of parabolic restriction. How should I say? So there is, I think, two very different ways how to think about this bigger quantum group. So the one way is I have this generic quantum group, so generic Q, and I have different ways of specializing. So I produce them. The other way that you can think about this is given a Nichols algebra, then you can ask, are there larger Hopf algebras? which project to this Nichols algebra. So something you want to ask sort of everything between the tensor algebra and the Nichols algebra. And of course, there's incredibly many. And now you can ask, are there suitable ones? For example, still finite dimensional ones. And that's a problem that is systematically studied in papers by Anchiono and Danuszkiewicz and so on. It's called post-Nichols algebra and pre-Nichols algebra. And so I came across this some time ago because I looked at quantum groups at very small root of unities. Because in physics applications, I'm always a little bit, I'm an algebraist, but I'm always a little bit interested in these physics applications. You have cases like, for example, you have weird cases like UQG2, where Q is a fourth root of unity. So you can define this. Lustig defines this, but he just defines it. And then he says, well, the small quantum group is defined by taking the simple root so-and-so and just take everything that's generated. But he doesn't make a statement sort of what is the space between the large guy that you get from specification and the small guy that you get from the generated by simple roots. So here it's not true that all root vectors are generated by simple roots. Namely, you have here an E1 and an E2, but then there is an E1, 1, 2, but this is not generated by this. So if you look at the braiding and the Nichols algebra is the same as UQA2, right? Because I mean, what is it's this, right? Sorry. It's here Q to the 6. I think it's like this. But suppose Q to the 4 is 1, then it looks like SL3, right? There's no difference. It's a 3 here. There is plus, minus. So as a braiding, it's the same. But if you look at the construction of Lustig, he actually writes down a larger algebra because it contains still this guy. So what you have here is a very, very non-trivial extension of sort of this guy. It has some of this additional generators somehow sitting on top. This is this article, Lustig quantum group for small roots of unity, communication in contemporary mathematics. So there's a couple of, it's actually, they're toy models. In large Q that doesn't happen, but for small Q you have this sort of, and again somehow they come from larger root systems, but you only see part of it in Nichols algebra. And I think this is a typical thing that should appear as a counterexample at some places, because what you think usually is not true in these cases. Somehow if you go through Lustig's papers, at some point he starts assuming that Q is large enough, and there is some space between what was done before and what is done after, and this space is basically these counterexamples.
Could I think about this extra generator as some non-trivial derivation? So I extend by not, so I have some outer derivation and I add.
Yes.
Okay.
You can also think that the non-trivial element in the Hochschild cohomology, right, in HH1.
Okay, yeah, then it will be exactly the same. Yeah.
Exactly.
And stuff like a central extensions appears, like if you are speaking about, well, if you have some outer derivations, could be have a non-trivial center. I try to understand, does guys like double extensions of Lie algebras appears?
Yeah.
Well, double extension, you can think about Kac-Moody, stuff like that.
Yeah.
When you add outer derivation and centers and pairs.
The Lie algebra, the Nichols algebra, of course, can then be infinite dimensional easily.
Yeah,
What you can always do is you can just write down the braiding matrix of what you want. You don't have to be finite dimensional. You can write down a braiding matrix, and you associate to it some root system and the braiding matrix. So I would always have this approach where you, of course, in physics you would always loopify the space, but what you can do is you just add another root and write down an honest Cartan matrix, an affine Cartan matrix, and just take the braiding and look what this generates, period. And then the Nichols algebra with some affine quantum group report.
Okay.
So you can just do that, but don't to make a loop space. Just try to add your additional roots, and then you have rank one more, and some Qij which belongs to an affine root system, and your Nichols algebra will be what you think it is. By the way, if you say central extension,
yeah, I remember.
Any central extension by a group looks exactly. So I prove also the opposite. Whenever you have a central extension of a Hopf algebra, it basically decomposes like that. It's like Schuh-Cover theory. It's always the fixed points and then some twisted sectors. Yeah.
Yep, great, thank you.
Okay, you're welcome. Thanks for the interest. Is there other questions?
I think yeah, that might be the finish of it. Yeah. Okay, then. Yeah. Thank you very much for an excellent talk.
Thanks. And we keep in touch about the stuff we discussed, and I will look at the reference also that was given to me. Thank you. And if you have questions, feel free to write an email. Yeah.
Fantastic. Great. Yeah.
Thanks a lot. Thanks for the invitation. Bye.
So next week, not next week, I should say, it's this Friday, we have the Velki seminar. Exceptionally on the Friday, it's going to be Thomas Weber from the University of Piedmonte Orientale, Amedeo Avogadro. He'll speak about principal differential calculi over projected spaces, and this will be in person in Jitna as usual. Okay, so hopefully see you all then. And yeah, thanks again.